Hello there, Mr. Sutton here with the AB Calculus 616 classwork problems on free response area and volume. For this non-calculator free response problem, we're given these two functions f and g, the square root of x and 6 minus x, and they gave us a nice little graph here. And these functions, along with the x-axis, bound the area r here. So for our first part of the problem, we just want to figure out the area of r. Now, there's two ways to do this. If you integrate with respect to the x-axis, you could do two different integrals here. So you're going to have to switch because your top function is switching about 2/3 of the way through. Another way to do this is to integrate with respect to y, and then you only have a single right function versus left function. Now, in terms of making the decision, I'm going to go ahead and integrate with respect to y. I'm going to have to do some rearranging of functions in the beginning, but I see that in the very next part of this free response problem, they want me to integrate again with respect to y anyway. So I'm just going to get it over with on this step and save myself an integral, especially since I have to do this thing out by hand. So I'm going to start by rewriting these functions in terms of y. For this first one, I'm just going to square both sides to get x equals y squared, or f of y equals y squared, we could write this as. And for this other one, I just add x over here and subtract y, so I can write g of y rather equals 6 minus y. And now if I'm integrating from bottom to top, using right minus left reasoning, I'm going from 0 to the y value 2, which they were nice enough to give me on the graph there. So area is going to be 0 to 2 of, and now we're going to do right minus left. And I'm actually going to write it all out because, again, I have to do this by hand. So 6 minus y squared dy is what all of that looks like. And now let me do my antiderivative going from left to right here. So I've got 6y minus, this is going to be 1/2 y squared. And then this bumps up to a 3. Dividing by that, we've got minus 1/3 y cubed, all evaluated from 0 to 2. So we've got all of this stuff with 2 plugged in, minus all of this stuff with 0 plugged in. And at this point, you're actually done. You've got all constants. You could just stop here and get your points and move on to the next part of the problem. Or if you wanted to simplify this second brackets here is just going away completely because everything's being multiplied by 0. For the first one, we have 12, and then this is, let's see, half of 4, so we're subtracting 2. 12 minus 2 is 10. Minus, we have an 8/3 over here. Well, this is really 30/3 minus 8/3, which is 22/3 for the final simplified answer. For this part of the problem, they're telling us this region R is the base of a solid. For each y between 0 and 2, so they're really just spelling out the interval here, cross-section of the solid taken perpendicular to the y-axis is a rectangle, whose base lies in R and whose height is 2y. They want us to write but not evaluate an integral that gives us the volume of our solid. So we have these rectangles, these left to right rectangles. The base is just the distance across this area, and these rectangles are kind of popping out of the screen and being added together to get the volume. So for this one, we're going to start with the area of the cross-section. We can say a of y in general equals base times height. And for the base, again, it's just going to be the distance between these two functions going horizontally. So I'm going to be a little bit clever about this. I rewrote this g of x function as g of y on the last problem. Same thing with f of x. I rewrote that as f of y to be in terms of y. So for my base, to get my left-right distance here, I can just say g of y minus f of y. And then for the height, well, they told us the height was 2y, so we're just going to literally put in 2y here. And now for the volume integral, the volume is going to be the integral from 0 to 2. We're going from bottom to top of, well, just the area, so a of y dy. And since they said I didn't have to evaluate this, and I already told you what a of y is here, I'm actually done with this part of the problem. For this last part of the problem, they're telling us there's a point P on the graph of f, at which the line tangent to the graph of f is perpendicular to the graph of g. They want us to find the coordinate of this. All right, well, if we have a point where the line tangent is perpendicular to the graph of g, Basically what we're saying is there's some place on P where f prime and g prime are opposite reciprocals. So we can say f prime of x equals negative g prime of x to the negative 1. Again, these are going to be opposite reciprocals if we have perpendicularity going on here. Perpendicularity, I guess, if that's a word. So f prime, we know that that is just the square root function differentiated. So that's really x to the 1/2 derivative. That's going to be 1/2 x to the negative 1/2. And how about g prime of x? Well, since that's just this line here, the derivative, g prime is negative 1, so we want negative 1 to the negative 1. A whole lot of negatives here. Okay, so this is really just going to be negative reciprocal of negative 1, which all just comes out to positive 1. And then I can multiply by 2 and raise both sides to the negative 2 to get rid of this negative 1/2. So I have 2 to the negative 2, which is 1/4. So this is the x value where the tangent line for the f graph is perpendicular to the graph of g. So to get the other piece of this, I have to actually find the y value of this point. Now they said that this point was on the graph of f. That means to get the y value, I need to plug this x value of 1/4 back into my f function, which gives me a value of 1/2, square root of 1/4. So then my point P is 1/4 comma 1/2. On this problem, we're given this f function, this polynomial, and they gave us a graph as well. R is this shaded region in the second quadrant, and we have S bounded by the graph of f and some line, which they haven't defined for us except that it's tangent to the graph of f at x equals 0. So our first task here is to find the area of R. So we have f of x already. We can think about this as just going from left to right, doing top minus bottom function in an integral. But in order to do that, we need limits of integration. The region R definitely ends at x equals 0, but what's this first limit of integration? So to find that, we're going to have to look up in quadrant 2 where the f function equals 0. And for that, we're going to need the calculator. So I've entered this long f of x function in my y equals, because I don't want to do this by hand ever again. And for my window, I'm going to go between, let's see here, I think negative 2 to positive 4 might work. It might be too much, but let's try it out. So negative 2 to 4, zoom fit, zoom 0. Let's see if I get something like what they graphed out here. Okay, this doesn't look like it's going to be too bad. So that's pretty much what they graphed out. Let's go ahead now and figure out the x-intercept over here. So for that, I'm going to do second trace and 0, option 2. And let me go a little bit to the left of that and press enter. So my spider's moving very slowly today. All right, there we go. Enter, move it to the right, press enter, enter again, and we have an x-intercept of about negative 1.3731. So I'm going to represent that as P in my writing here, so I don't have to write that stuff again. And while I'm at it, on my calculator, I'm going to quit out of my graph, and I'm going to store that x value that I just got as P on the calculator, so alpha P. There we go. Next, to find the area, I need to take the integral from P to 0 of f of x minus 0, or just f of x dx. So integral from P to 0, f of x dx, and let's do that on the calculator now. So I'm going to do zoom 6, or zoom 9, no, math 9, there we go, this button. And then we're going from P, so alpha P, to 0. And let's see here, I entered this in my y1, so let me do alpha trace y1, and then dx, for a grand total of 2.903. For this problem part, I want the volume of the solid created when R is rotated about the horizontal line y equals negative 2. I'm going to start by drawing that line. That's down here. And when we have this visual, we see that we have this space between the axis of revolution and the bounded region. That means the cross sections of this revolution solid are going to be donuts. They're going to have that hole in the middle. They're going to be washers. So writing out my area of my cross section, I'm going to go with the formula a of x equals pi times big R squared minus little r squared. And then for my big R, my big radius, that's the distance between my axis of revolution and the part of the bounded region that's further away, so f of x up here. So to express that, I'm going to do f of x minus negative 2, or f of x plus 2. And I still have the pi outside, and I'm squaring now f of x plus 2 inside there. For my little radius, that's just the distance between this closer part of the bounded region and this axis of revolution. So that's just a distance of 2, and we're going to square that. And now for my integral, my volume, I'm going to say that I have the integral from p to 0. It's the same limits of integration as my area for r. And then I'm just going to do a of x dx in here. Now to do this on the calculator, I'm actually going to enter a of x in my y2 just to make it a little less unwieldy. So I've got a pi. This is f of x plus 2 squared in here. Glad I don't have to write that f of x function again. And then I'm subtracting 2 squared. Let me quit out of there now. And I noticed this input from before that I used to get the area of r. I'm actually going to arrow up and yank that input so I can reuse it, kind of, sort of. But instead of y1, I'm just going to put y2 in there. I have the same limits of integration, though. So let me do alpha trace and y2, enter, and that comes out to 59.361. For this problem, I want to write but not evaluate an integral expression that I could use to find the area of S right here. So to do this, my general strategy, I need to get a formula for this tangent line L, and then I need to subtract f of x from L inside an integral from 0 to, well, whatever this intersection point is. So let's start by getting that formula for the tangent line. So in general, that's just f of a plus f prime of a times x minus a, but a in this case is 0. That's our launching off point. So I'm going to write the formula initially like this. L of x I'm going to say is f of 0 plus f prime of 0 times x minus 0. And I actually have a way of getting all the values I need out of this because I've already got my f function in the calculator. To find f of 0, let me just do alpha trace and pull up y1, and I'll just plug 0 into that directly. And it comes out to exactly 3. Well, that's convenient. So this is going to be 3 plus, well, what's f prime of 0? I mean, I could take the derivative by hand, but, I mean, why bother? I've got a derivative function in the calculator. So I'm going to do math 8, and I'll do dx alpha trace y1. I want to take the derivative of f of x at x equals 0. Enter. And that is essentially negative 0.5. If you round it off even to 3 decimals, that's going to be 0.5. So that's what we're going to use. Or 1/2. I guess you could use 1/2. Either way, you're going to have plus 1/2. And is it positive or negative? It is negative 1/2. Okay, glad I checked. So negative 1/2 x. And I mean, you could say x minus 0, but that's just x. So there's our tangent line. Now we need to figure out where this tangent line intersects the f of x function. So I'm going to write L of x equals f of x at, I mean, clearly it intersects at 0 because it's tangent there at 0. But where else? To figure this out, I'm going to go into the y equals on my calculator, and I'm going to deselect this area function that I did in part B. I don't want to graph that again. But in y3, I'm going to put 3 minus, and let me do fancy fraction here, 1/2 x. There we go. And let me just do second trace and then intersect. So I'm going to figure out where my polynomial, well, it's not really a polynomial trig hybrid, and my line are intersecting. So there's the first intersection at 0, and here's this other intersection. Let me move my little spider over here to get to the bottom of this thing. And enter, enter, enter. And that comes out to about 3.3899 if we round that off to 4 decimals. And I'm going to call that number Q because I don't feel like rewriting it. Now, I would also store this on my calculator, except they said write but do not evaluate. So I'm never actually going to need to use this calculator in this problem. I'm just going to need to refer to it. So now my integral expression to find the area of S, I can say the area of S equals the integral from 0 to Q of L of x minus f of x dx. On this problem, I'm given this graph with two functions, 4 minus 2x and this rational function here, and they're giving us R as the region bounded by these two functions in the y-axis. They want us to find the area of R for the first part of this problem. So I'm going to begin all of this, since this is a calculator problem, I'm going to begin all of this by renaming these functions. I'm going to call this rational function here that's having a positive slope, I'm going to call this one f of x. And I'm going to call this other function here g of x. That's going to be 4 minus 2x. And while I'm at it, I'm going to enter both of these in my calculator. So there we go. I've entered them both in y equals. F is in the y1, g is in the y2. Now I don't have to rewrite them again. For my next step, I need to figure out where these things are intersecting. I'm going to eventually take the integral from here to here of top minus bottom to get this area, but I need to know my other limit of integration. The first one is clearly 0. If you're not sure about that, you could plug 0 in here and you'll get 0 over 1, which is 0. But we need that other one. So I'm going to say f of x equals g of x, and now I'm actually going to solve it on the calculator. So I'm not entirely sure what my window should be for this, but since this is the function 4 minus 2x, that means this down here has got to be x equals 2. So I'm just going to go ahead and make a window from, we'll say 0 to 2, and then let me zoom 0 that, and that ought to give me essentially the area that I'm looking for. So there was my f of x, there's my g of x, and now I'm going to find the intersection right here. So let me do second trace, option 5 for intersect, and let me arrow over there, enter, 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 and that gives us a value of about 1.4877 if we round off to 4 decimals. And on paper, I'm going to refer to that as the x value p, so I don't have to keep writing it. I'm also going to go on my calculator, quit out of the graph, and I'm immediately going to store that as alpha p. So now I can use it in both places without rewriting all of it. Okay, so to find the area then, I need the integral from 0 to p of top minus bottom. So that's going to be g of x minus f of x dx. And to do that on the calculator now, let me do math 9, integral from, we said 0 to p, so 0 and then alpha p. And then in here, g of x minus f of x on my calculator, that's alpha trace y2 minus alpha trace y1. Let me go back to the screen there. For some reason, it wanted to graph stuff. There we go. Here we go, alpha trace y1, and then we'll have dx. Press enter. That's about 3.215 if I round off. And that's the area of R. For this next part, they want us to find the volume of the solid generated when R is revolved around the x-axis. Since I'm going around the x-axis, you'll notice that we have this space between the axis of revolution and the bounded region. That means I'm going to have to use washers. So my cross-section area I'm going to write as a of x equals pi times big R squared minus little r squared. Big R, that's going to be the distance from the x-axis to the part of the region that's further away. That's the g function up here. So I'm going to write pi times g of x squared. And then little r, that's the distance from the x-axis to the closer part of the bounded region. So that's just f of x that I'm squaring and subtracting in there. And notice that I wrote a sub 1 of x equals all this because I'm going to have a different cross-section area formula in part C, so I don't want to mix it up with this one. I was just kind of thinking ahead here. All right, I'm actually going to enter this in my y equals on the calculator now. So I'm going to put this in y3. I've got pi times, and then I did y2 squared, that's g of x squared, minus y1 squared, that's going to be f of x squared. Quit out of there. And since I've got the same limits of integration as my r function, since this is the integral from 0 to p of a sub 1 of x dx, what I'm going to do on the calculator is I'm actually going to arrow up to my prior input to find the area of the r function, or the r area, and I'm just going to delete the stuff that I had in here, and instead I'm going to do alpha trace y3 now. That's now a of x that I'm integrating from 0 to p. Press enter. That's about 31.885. For this part, they're telling us the region R is the base of a solid, and for this solid, each cross-section perpendicular to the x-axis is a square. We want the volume of that solid. So let's start by getting the cross-section area. The limits of integration are going to be the same. It's just the limits of integration for R, which was 0 to p. Really glad we stored p as a constant at this point. But for the cross-section area, since these are squares, let me start with a sub 2 of x equals s squared. And again, I already had a different area formula in part B, so I'm naming this a little bit differently so that it doesn't get confused with that one. Now for S, the side of the square, since these squares are going perpendicular to the x-axis here, that means I just basically need top minus bottom. So that's going to be g of x minus f of x that I'm squaring here. And let me go back to the calculator to do that one. But before I do that, my general setup, my volume, integral from 0 to p of a sub 2 of x dx. All right, let's do this. So I did some work in my y equals. Big surprise there, right? That's just kind of my style. I did g of x minus f of x squared in y4. Now, quitting out of there, I'm going to go back to this prior input that I used to find that other volume, and I'm just going to kind of cut and paste that, and I'm just going to replace y3 with y4 because that's where I stuck this second area formula. So alpha trace y4 now, and now enter. That's going to be 8.997.